assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
This question says a sample of SO3 is introduced into an evacuated sealed container and heated to 600 Kelvin. The following equilibrium is established. The equation is here. It says the total pressure of the system is 3 atmospheres and the mole fraction of O2 is 0.12 and asks us to find Kp, or the equilibrium constant with respect to pressure. So let's draw an ice table. Again, it doesn't tell us anything about the starting conditions, so I'm going to put this in terms of moles of gas, and I'm just going to give this an arbitrary value of 1, some amount of starting material. What number you use isn't really important, it'll all be relative at the end, but I'm just going to use 1 to simplify the math. And we have none of these two gases. We can write the change, minus 2x here because of this 2, plus 2x because of this 2, and then just plus x for O2. And we can write out these equations as so. These are the equations for the equilibrium number of moles of each of these gases. Let's calculate the total number of moles. I'm going to call this NT. Let's get it equal to the sum of these three equations. So 1 minus 2x plus 2x plus x equals 1 plus x. And I can express each of these equations in terms of mole fraction, but first I'm going to do it for O2 because I know O2's mole fraction. So the mole fraction, this big chi symbol of O2 equals the number of moles of O2, which I have as x in that equation, and the total number I just calculated is 1 plus x. And we know this is equal to 0.12. If I solve for x, I'll find that x equals 0.1364. Then I can calculate the number of moles for each of these at equilibrium by plugging x in here, and I get 0.7272 for SO3. I get 0.2728 here for SO2, and I get 0.1364 I just calculated for the number of moles for O2. So just continuing these columns down, this is the number of moles here. From this, I can calculate the mole fraction of each of the parts. So the mole fraction of each of these parts is this number divided by the total, and the total is 1 plus x, which equals 1.1364. So this equals N total. So if I divide each of these three values by the total, I can get the mole fraction of each of them. Here it is 0.64. Here it is 0.24. Here it is 0.12, what I was given. Now, if we look at the equation for PV equals nRT, if I were to convert each of these values, if I just convert each of these from moles to pressure, I could have done so, but I don't know this volume here. I could probably calculate it with some work, but what's easier is there's direct proportionality between pressure and number of moles. So if I take the mole fraction, I can also take the fraction of the total pressure for each of these gases. So if the mole fraction is 0.64, or 64% of all of the moles of gas at equilibrium are SO3, then 64% of the total pressure comes from SO3. So if I were to multiply 3 times each of these fractions, I would get 1.92 atmospheres for SO3. I would get 0.72 atmospheres for SO2, and I would get 0.36 atmospheres for O2. Finally, now that I have the partial pressures at equilibrium for each of these gases, I can plug these values into this equation I wrote out earlier. If I did that, I would find that the equilibrium constant with respect to pressure is about 5.1 times 10 to the negative second.